Hi and welcome back to another LeetCode video. We're currently going through the one-dimensional dynamic programming problems on LeetCode.io. We have completed the previous two problems, which were easy. The climbing stairs and the min-cost climbing stairs problem. We're going to have a look at the house robber problem next, which is another variation to the previous two problems. However, the difficulty is a little bit higher. So let's see, how you can solve this one. Let's just try to understand first what this is about. So you're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that the adjacent houses have a security system connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. So we're given an integer array nums representing the amount of money in each house. Return the maximum amount of money you can rob tonight without alerting the police. And then it goes on. So money is between 0 and 400. We have at least one house, etc., etc. So this is very similar to what we had before, except now it's not that we can take one step or two steps. Actually, we have to make sure that our step size is at least 2. We cannot visit two adjacent elements or houses or steps, if you will. So let's take this. Let's maybe take this as an example. Second one. Pasting it here. Right. Paste it again. Come on. There we go. And I'll make it a little larger so I can draw on it. Cool. So we cannot visit two adjacent houses, but obviously we want to visit as many houses as possible, right? So we could say we want to start at house 2. Well, in that case, we cannot visit house with seven money in it. We can only decide to visit the house after, and then the one there. So we could also skip one house, and instead of visiting the house with value 9, we could go to house 3, but then we're done. So the question is, well, how do we compute how much profit we can make? Well, it's simple. In the beginning, we decide where do we want to start? What are our starting conditions? Do we want to start at index 0, or do we want to start at index 1? And then all we need to do is we need to basically decide if we want to take 2 steps forward or 3 steps forwards. Those are the two decisions that we're going to make at every single step. And to make it a little bit more simple, you can envision this as an array as follows. So when we build up our maximum loot, well, the maximum loot will be when we reach the end, right? So when we step out of the range of houses, and then we will have reached the goal, and whatever the maximum amount of money is that we collected until then will be our result. So, and the way we could do that is we could say, well, we could do some padding as we always do. And when we compute, well, when we decide to visit this house first, we could say that we either came from the house 2 steps ago, and we're adding 2 to our loot back, or we came from 3 steps ago, because we could not have come from the previous house, because that would have triggered the alarm. So that's not possible. Now, if we want to compute what's the maximum loot that we can get by visiting this house, right? So we get 7 loot plus whatever was 2 steps ago or 3 steps ago. So the maximum of those two. Obviously those are 0, so there isn't really anything to add. But I guess you get the idea. Let's do one more step so that we see the case where we actually have some predecessor value. So if we compute how much loot we can get by visiting this house and houses that we could have visited before, so we're getting 9 as that value, plus what did we have 3 steps ago? Well, 0. But what did we have 2 steps ago? Well, 2. So it's actually 9 plus 2. That's the maximum loot we can get when we visit the house in order, and we then visit house 9. So that's going to be 11. Similarly, yeah, let's do one more step. Let's use this color. So if we visit this house then next, actually I'm going to do both. So this house next. So we get 3 plus the maximum of the house 2 steps ago, which is this one and that one. So, and the maximum is between 2 and 7, so it's 7. So 3 plus 7, which will be equal to 10. So that's our maximum here. And then finally at the very end, we get, well, what's the maximum value we can get when we get here? Well, it's 1 plus the maximum between 11 and 7. So we get 12, right? And this is actually our result that we're supposed to get. So yeah, you can see again, you have this optimal substructure where you can decompose the computation of the final solution into computing the solution to overlapping subproblems. And the overlapping subproblems are basically, well, what is the maximum loot that I can get if my street only had house 2 on it, right? This is everything up to here. Then you compute the next subproblem. What is our my maximum loot if I can visit all the houses up to the second house with the value 7? That is this. This is then the result. And then basically every subproblem, you add one more house, and then in the end you have all of the houses and you get your full solution. So that's how you decompose the problem into into a dynamic programming problem. So now let's start to implement this. Well, you've already seen that we can we can create our loot array, right? So, and we would have to use O of n space and time for that. And we would initialize our loot array with 0 so that we're able to access the 2 predecessors that we're interested in, the houses 2 steps ago and the houses 3 steps ago. And we just iterate now over the range of all of the houses, ling nums. And what we'll do is we will, well, compute the subproblem solution, which is basically the max loot at the current position minus 3 and current position minus 2. So that's 2 steps ago and 3 steps ago, plus the loot in the current house, right? And we just append this to our loot array. So at every step of the for loop, we are computing the solution to an overlapping subproblem using the solutions of the previous subproblems. That's what we do exactly here. Cool. And yeah, and then finally, at the very end, we just have to return the maximum. And now the maximum can be in any of the last 2 houses, right? Because the last one here, that took into account the houses up to minus 2 and minus 4, minus 2, minus 3. But the one before took not the house, not this brown house into account, but rather the houses up to which index was it? To where the value was 7, where the value was 2. So you can actually not take just loot minus 1, because maybe you went on a rampage path where you only went to house at position minus 2. So what you really want to do is you want to compute the maximum of all the loots of the last 2 houses that you were able to visit. And if the condition was different here and you can only visit houses that are at least 2 steps apart, this logic would change, right? So we would have minus 4 and minus 3, and then we'd also have to adjust that. Yeah, but I think you get the idea. So this is the first approach. Of n time and space, runtime error. Did I make it? What is in range? Okay, so there's a typo in there. Why is this not correct? Max loot I minus 3, loot I minus, oh, sorry. It's not I minus 3, it's minus 3 and minus 2 because we're growing the loot array, right? Every step. So if we put the I in there, we get an off by 1 or off by 2 error. Right, so that will work. And I'm going to show a couple of other implementations because there are many different ways of how you can do this. And you're not always going to be as lucky to be able to see this decomposition right away. So maybe you come up with one that's slightly different. So this one we computed from the front, right? But there are also other approaches. So the first one is, well, how can we get down this space complexity? Clearly, in the end, we only need the last two values, right? So why don't we do it time, sorry, OCD moment, or time and O of one space. Sorry, time and space. Like this. Well, we only need 3 elements in our loot array, right? So in the end, if we only keep the last 3 elements in it, it's a constant space. So let's do that. So the way we can do that is by simply saying loot at position 0 is going to be loot at position 1. So we're basically treating it as a sliding window where we just shift all the numbers one step to the left that are in the loot array. And at the end, we add a new one. So we say loot 0 is loot 1, loot 1 is loot at position 2. And then at position 3, we're going to add the new value. So we say loot at position 3 equals that. So if we run this now, yeah, we could maybe simplify that a little bit. Let's just say value. So this is the new value that we're going to compute. Oh, maybe I just had a closing bracket error here at the end. Yeah, unmatched. Yeah, sorry. So you can write it like this. I mean, maybe it's easier if you write it like this. You know, we could just say it's loot from position 2 onwards plus whatever this maximum is. So that would be another way to write it. However, the second way now creates a new array, whereas this one really just assigns the values inside there and reuses the existing one. Loot 2, max loot at I, index out of range, loot 0 equals loot 1, loot 1 equals loot 2, loot, 0, 1, 2. So this needs to be a 2. Yeah, that gets tedious when you start to mess around with these indices. So, but yeah, okay, so this looks like it'll work now. And that works as well. So both of these approaches are iterative approaches. They're nice, and I think this one is actually the optimal one of n times O of one space. I'm just going to show you anyways maybe an iterative approach. So a way to do that would be to formulate this problem as a recursive problem where you just have a little helper method. We're going to pass into the helper method. What should we pass into it? Let me think real quick. We could pass in just how many steps we need to compute in our recursive call. So we would call return helper, and then we would say we'd start. Well, we can say that we want to. Let me think. How could I do that more effectively? Well, we know that we have the decision to start at index 0 or at index 1. So what we could do is we could say, let's start at index 0, and we will keep track of what is the current maximum loot that we can get. However, we also need to start at index 1 and see where we get. Because if you remember, if we visit a house, we cannot visit the next house. So there are 2 ways of starting here, either from the house at the first position, at this one, or here. So those are the 2 cases. So if we use a recursive helper function, we also have to start from both of these base cases where we start. So we're going to pass in basically the index of the house that we're visiting, and we're going to pass the maximum loot that we currently have, or max loot, or could just call it loot, right? Now we have to check if we've reached the end of the houses. So if I is larger or equal than nums, right? In that case, well, we're done. We can't get more than what we have. So we're going to return loot as our answer. Now, if that is not the case, we can actually visit the current house at position I, and we can increase our loot. So we say nums at position I. And what we have to do now as well, now we have two choices again. The same choice that we have when we started entering the recursive function. We're just going to return the maximum between calling the helper from the current position plus 2. So we're jumping over one house, or plus 3, that is where we jump over 2 houses. And we're always going to pass in our current loot. So what this will do, it will, let me see if let me just scroll downwards a little bit. So those are all our possible positions or values for I. We will have 2 initial values, so we will start here. So this is one start, and this is, this is the first start, and this is the second start outside of the recursive function. Now inside that function, we will call recursively I plus 2, so we will call a recursion on this index of I and on this index of I. And here we will call a recursion on this index and on that index. And of course, from here on, we will call a recursion on this one and on this one, which doesn't exist, which will be caught, right? So the thing is, you can see that actually we're doing computation twice here. And we don't really want to do that. And the longer the array gets, the many different ways there are to reach the nth cell. In fact, that was the problem that we solved earlier with one of the other one-dimensional dynamic programming problems, where the number of ways to reach a certain step was basically a Fibonacci sequence. Now here we're taking different step sizes, so the sequence is slightly different, but it's a very fast growth. And the longer our list of houses is, the more computations we're just going to do multiple times. So what we want to do, well, we don't want to compute the same result when we call helper with the same index and the same current loot multiple times. So the trick here is we're going to use a cache. In Python, you can do that with the @cache annotator. It remembers these 2 input parameters, those are integers. And whenever this function is called again with the same parameters, it doesn't execute the function body, but instead returns what this function returned previously when it received those 2 parameters. So it's essentially caching mechanism. Now, because we only have n elements in our numbers array, that also means that the cache will never have more than n elements. So this approach actually will have O of n space, this recursive one, also because of the recursive calls, right? So it will use O of n stack space as well as O of n cache for the cache. But it's also O of n time because it needs to iterate over all of the elements. Even though it doesn't iterate, it does it recursively. But yeah, let's just see, let's just show and demonstrate that this works. So this one is accepted. And that one is also accepted. So this approach is very similar to, it's essentially the recursive version of our first one where we didn't have a space optimization. We start building up the loot array from the front. You will see when you look at some solutions, there's also another way of how to solve this problem. And that is by trying to build up the solution from the back. And I just want to show this one as well. So this time, what we will do is we will have, let's see. We will use the same caching techniques for the same reasons. But what we will pass in is, well, what is our Well, we will pass in an index I essentially. But we will start from the back of the array. So we will pass in the length of nums, -1. And we're also going to pass in the house position before that, which is n-1, length nums n-2. So let me just go to the visualization real quick. So now in this example, our two starting points, so this is our first starting point, and this is our second starting point. And then we just say, okay, in order to compute the result from this, all we need to do is the current value at this position plus the value from the maximum of these two positions, right? So we can do a recursive call backwards, and we will terminate when we reach one of those positions where we had the 0 padding in the beginning. That's where we will terminate. And similarly for this position, we will build our result by looking at the two predecessors, skipping the immediate predecessor. So it's kind of the same idea. I hope you can see that. So, but we build it up from the back. So if n is smaller than 0, we're just going to return 0. Otherwise, we're going to return the maximum between helper at position and I minus 2 and I minus 3. But we're also going to add nums at position I. So that's how we would do that. And we're also doing the caching again. We don't have to have this initial array of zeros because we catch that with this case. So if I is smaller than 0, we just return 0. And it's actually also going to be cached. So I guess it will be stored somewhere. Yeah, and otherwise we just return that. So let's just run this to demonstrate that this also works. And it works. And if we submit that, it also works. So yeah, so that is it. Those are 4 different approaches. You can approach it recursively. When you approach it recursively, it's going to be difficult to optimize the space complexity. But if you do it iteratively, there's actually a way of how you can reduce the space. And how much you can reduce the space really depends on the dependency between the problems and the subproblems. In our example, we had that every subproblem was dependent on 2 subproblems to compute it, right? And those were the predecessors at -2 and -3, right? So we kind of had kind of a tree structure. And that meant the number of children that the problem depended on was kind of the space complexity. You can run into problems, I don't know, where you maybe have a 2-dimensional thing, and then the solution of, oops, this is a great drawing, by the way, where the solution of one thing depends on like n or m other subproblems. So there you will have a space complexity that is then maybe dependent on m instead of on a constant or something. And then you compute this solution, then you compute the next solution, etc., until you reach at the end a final conclusion. But yeah, it's the same thing, just in 2 dimensions then. So that concludes this little problem. I think it's a really cool one. And with these dynamic problems, I would always recommend try different implementations, different approaches, because one of the most confusing thing about them is really that you actually have that many ways of approaching them. And the art is really to understand how to decompose the problem into subproblems. You start with, what if I have an input of length 1, length 2, length 3? Can I compute the result, right, depending on the previous results? Yeah, this video is way too long. I'm going to stop it here, and I hope you have time implementing this.